Okay. Hello, everyone. My name is Yijie Li. I am now a PhD student from Shanghai Jiao Tong University, and I'm going to present my paper, ScreenID, Enhancing QR Code Security by Fingerprinting Screens. QR code means Quick Response Code, which is comprising of black and white blocks, specially recognized by its 3 position markers. QR code now is widely used all over the world, such as United States, China, and Australia. On account of its convenience, QR code is becoming popular. It has many applications, such as mobile payments, advertisements, social e-cards, and so on. For a payment scenario, the camera on the cashier scans the QR code displayed on the screen and the transaction then is permitted. Mobile payments are gradually growing up, especially in China. In China, more than 45% of the population use mobile payments, and the value of mobile payments is growing up too. However, QR codes suffer from security concerns. Recent studies present the replay attack in mobile payment scenarios. The replay attack means that when a customer shows the payment QR code on the screen to the cashier, some of the customers in line will prepare the payment barcodes in advance. Meanwhile, the attackers can obtain the QR code by taking a picture using cameras or installing malware. Once the attackers obtains the picture of QR code, there is no need to decrypt the QR code. He only needs to simply submit the captured QR code to other cashiers or customize the software to complete an illegal transaction. Therefore, the user's property will be compromised. So, how to deal with this problem? Researchers have done lots of work to prevent replay attacks. PostOps double-check the token and Post ID to guarantee the safety. Endpoint utilizes the screen brightness level as the fingerprint token. MQR code uses more pattern to encrypt the original QR code and decrypt it at specific position. However, such works all require specific environments, fixed position, and will change users' habits. Unlike these methods, our approach utilizes hardware fingerprints, which allows the user complete freedom. Our solution is to encode a hardware fingerprint bound to screen into QR code. Although the attackers obtain the QR code, the fingerprints for attackers' screens do not match that encoded from an authorized screen. Therefore, the transaction will be terminated. The hardware fingerprint is PWM frequency. Pulse width modulation flickers the screen at a particular frequency, which we call PWM frequency. It controls screen brightness by regulating the ratio of screen on time in each cycle. You can see from the picture on the right, the lower the bright ratio is, the darker the screen brightness. When capturing the screen, the CMOS in camera samples row by row at different times, which means that there existing a sampling interval between 2 rows, resulting in black and white stripes. Since human eyes are insensitive to high frequency, we do not notice the flickering. To verify if the PWM frequency can work well, we studied the feasibility of utilizing PWM frequency as a fingerprint using light sensors. Preliminary results show there exist differences across screens, even for the same model. Also, the fingerprint is stable across time and distance. Here is a brief demo at low exposure across 4 screens. Different patterns shown on screens for the reason that they are of various PWM frequencies. In order to extract the PWM frequency from screens, we face several challenges. First, the patterns for OLED screens changes over distance and angle, but LCD screens are not. As you can see from the picture on the left, it is because that LCD screen lights using only a single backlight, whereas each row of OLED screen lights asynchronously. Second, the rows in the camera sample rows on the screen may be not one-to-one correspondence for the reason of distance and angle. The sampling process of each row also performs at different times. Therefore, we must model the communication in both temporal and spatial domains. Third, the preliminary study illustrates 0.1 Hz can differentiate 99.3% screens. In order to achieve the goal, high-frequency resolution is necessary. To overcome the challenges above, we propose ScreenID system. The overflow of ScreenID is composed of two main modules, an encoding module for screen and a decoding module for the camera. We first encode key information, including PWM frequency and the latency across rows that we call delta S into a fixed-sized QR code. Then, capturing a photo to calculate the rotation angle by using position markers and compute projection ratio as a fraction of length of pixels along the original QR code. Finally, we record a video, extract contours of screens, concatenate multi-frames for improving frequency resolution, extract the PWM frequency using downsampling Chirp-Z transform, and verify if the screen is authorized. In this section, I will show you our performance evaluation. We generate 50 QR codes for 50 smartphone screens. 10 are LCD and 40 are OLED screens. 5 smartphone cameras are used in our evaluation. We displayed 40 QR codes, while 10 for verification, and the other 30 selected randomly for attack. We defined the metrics, the true positive rate to evaluate verification rate, and the false positive rate to evaluate the attack success rate. Firstly, I will show you the micro benchmark to evaluate the number of frames, camera configurations, and the threshold selection. These two figures show our proposed method. Downsampling Chirp-Z transform can successfully recognize the PWM frequency within 60 frames, which only takes 2.5 seconds overall, better than other schemes. These two figures show the impact of camera configuration. We set the exposure time to 0.3 milliseconds and set the ISO to the highest. For threshold selection, we should know about that when the threshold becomes larger, the true positive rate and the false positive rate both become larger. The higher the true positive rate and meanwhile the lower the false positive rate, the better the system works. Therefore, to consider a better trade-off, we select 0.03 Hz as the threshold, while the average true positive rate is about 94%. The false positive rate is below 0.8% in our dataset. Secondly, after setting the parameters above, we evaluate the overall performance of ScreenID. The average true positive rate is 99.7% for all screens and 95% for the same model. The false positive rate for the same model is lower than 1.5%, and for other models, the false positive rate is 0%, respectively. It shows that the proposed system can successfully enhance the security of QR code system. At last, we evaluate the robustness of ScreenID on the various impact factors. From the picture, the true positive rate is above 99.5% when the brightness ranges from 10% to 90%. When the brightness is 100%, the screen is always on, so it doesn't flicker. The true positive rate is 100% when the distance is 10 centimeters to 18 centimeters, which is reasonable for the user's habit. For the rotation angles and ambient light, the ScreenID is robust. When the offset angle is less than 5 degrees, ScreenID performs well, and the users can easily put the phone within 5 degrees. Moreover, It demonstrates that ScreenID can successfully prevent from being sniffed in other viewing angles. This validates the robustness of our system. In summary, we will have the conclusions that first, we demonstrated the feasibility of using PWM frequency for fingerprints, which can successfully enhance QR code security. Second, we proposed a ScreenID system, which incurs no additional hardware and no requirements for user behavior. Third, we proposed to model the interaction between the camera and screen in both temporal and spatial domain and achieved high accuracy. Fourth, we conducted exhaustive experiments and demonstrated that ScreenID system is robust under a variety of operating conditions. That's all my presentation, and thanks for watching.